Hi, everybody. Thanks so much for joining us today. We're so pleased to have you here for our next expert lecture with Dr. Marilyn Smith. Um, she is the director of the Vertical Lift Research Center of Excellence at the School of Aerospace Engineering at Georgia Tech. She received her PhD from Georgia Tech in 1994 while working in fixed and rotary wing industry from 1982 to 1997. She joined the School of Aerospace Engineering in 1997. Dr. Smith performs research in the areas of nonlinear computational aeroelasticity using CFD and the integrated multidisciplinary areas of unsteady aerodynamics and acoustic fluid structure interactions across rotating and fixed wing vehicles and systems. Her recent research also includes award-winning development of nonlinear reduced order models for design and modeling and simulation. Her research sponsors include all branches of the DoD, NASA, and DOE, ARO, ONR, and NSF, as well as industry. She was named a fellow of the AIAA and the Royal Aeronautical Society and a technical fellow of the American Helicopter Society, AHS, now VFS, for her research in those areas where she has co-authored or authored more than 200 publications. We're so pleased to have you here, Marilyn, and thank you so much.
Hey, thank you. I'll try to share my screen now so we can jump right into everything. Let's see, share. Okay, and slideshow. Mhm. Let's see. Wait. All right. Hopefully everybody can see the slides. Okay, if there is any issues, please sing out. Um, so I'm going to talk today about aerodynamics design and analysis. I can't do everything, obviously, but hopefully I could touch on some of the more pithy issues, and we can see, what questions you have at the end. I have some codes and stuff that I recommend, and hopefully you will see enough to understand and identify any issues you might be having. And if I don't talk about something, feel free to ask at the end. Even though we're talking about aerodynamics, because we're talking about a vertical lift vehicle, uh, aerodynamics is usually just combined together with structures, structural dynamics, and aeroelasticity to become aeromechanics. And so we usually don't divorce them in the rotor world. However, I'm going to try to focus just on the aerodynamic parts of that today. I know the audience is very diverse and maybe not even online, but looking at later. If you do look at the video later and you have questions, my email is right here at the bottom. Feel free to shoot me an email and I'll try to answer as much as I can. I can't spend the time to help you do your designs or anything for various reasons, but very happy to answer any questions and make recommendations. Now, if you're going to achieve those GoAERO goals, which are quite interesting and challenging, aerodynamics is not the only thing you need to do. So please, please, please make sure you have a nice, diverse team. You need to do not only aerodynamics, but structures, flight mechanics, and controls. You need very much to look at safety and reliability. Do not put those off. Those are right up at the forefront, not just because of the task, but because of, you want your vehicle to get to the location. With this is rescue operations, so you can't really lose your vehicles. Don't forget to look at novel and disruptive technologies, but don't rely 100% on them. Okay. Look at innovations from fixed wing, rotorcraft, and even non-flying vehicles. I've helped do our design teams for the past few years. And so, we look at a lot of different things, and we've gotten some really interesting concepts from ground vehicles. These are just a couple of examples. This is from last year's team. AeroLA was our undergraduate team. This was a rescue mission last year for the VFS competition. Our undergraduate team, I'm happy to say, won first place, and our graduate team won second place. So we're really thrilled about that. But what I'm telling you today is the same thing that I tell them when they're doing their competition design. So, look at how different those two are. And if you look at the winning team from the graduate University of Maryland, it's not that different looking from our graduate design here. So, you know, take a look, but be open to new ideas. Now, let's talk first about design considerations for aerodynamics. First is conceptual design. That's what you're doing now. Um, Requirements and mission feasibility analysis is your goal here. Look at the RFP. Look also at requirements from either the FAA or EASA or the military regs. Okay, you have to look. Now, the guiding principle is what GoAERO put out, but look at these other things too, because if you're serious about taking GoAERO beyond just the prize money and making it a viable design, those other things you need to look at as well. Okay, don't poo-poo historical concepts. I can tell you that in as early as the 1940s through the 1960s, they had some great ideas. The problem is they didn't have the technology to make it happen. Okay, but those great ideas, I see things all the time. I read in papers and things, oh, this is a novel idea. And I was like, no, it's not. I've been around long enough that I've seen these things come and go. Everything is cyclic. So, look back and see what's going on. Make sure you do a technology assessment and some sort of decision process, either using a analytical hierarchy process, a morphology matrix, whatever you like to do. Okay. Now, your goal here is your sizing. You want to minimize your gross weight, minimize the power required, and make sure you can get the performance goals necessary for the RFP. Now, with that, your timeline is, again, I'm just giving you a generic here. GoAERO is what you're going to work to. But typically you'll use 6 weeks to 6 months. For more complex designs, you need to go farther out. More simple designs are closer to the 6 week side of the house. Please do not rush out and try to do RAND's CFD for this part of your design. You need to be doing a lower fidelity effort. You need to be doing trade studies. For if you have rotors, well, you will have rotors. You'll use momentum theory first, then probably blade element or blade element momentum theory. You'll use lifting line panel type codes for non-rotating parts of your design, which, you may have tails, empennages, fuselages, wings even. Then, you can go all the way to just using data from places like Horner, which is excellent reference, by the way, and panel codes, maybe a lifting line for wings. You're not going to do CFD here, okay? You need to be able to look at a wide variety of design spaces, okay? Now, for the computational tools here, though, you're going to be looking at codes such as RCAS or CHARM, VS-Aero, XFoil, AVL. For non-lifting, if you do want to do some sort of CFD and beyond this theory and panel methods, then you need to do what I call design CFD. Now, there's two offers out there that allow you to do that. One is called CGE. It's by Continuum Dynamics. And the other one is ROT CFD, which is from Sucre Helitech. Now, if you're interested in those, I can give you the details. I'm not going to, push or really talk about a lot of the codes here. I'm going to tell you more the concepts, and what you choose to use your code is what you choose. Okay. Now, for a full vehicle, if you want to look at the entire vehicle together to get some of your mission concepts, because you need to do that, then you could use FlightStream, which is developed out of Auburn. If you talk to them, sometimes you can, if you're a university, sometimes you can get a free license. GTAB is something from my group. It's not really for aerodynamics. It's an aerodynamics product, but it's used mainly for your controls design. Okay, but it can be used here in some instances. All right, so your goal here is to freeze your concept. This is when you're looking at all those different concepts. You want to freeze the concept. You've got an idea, you know, single main rotor, quad rotor, tail sitter, whatever you're planning to do. That's the concept that's frozen here, not the details. All right. This is why you don't need all of the URAN CFD. You're not there yet. You don't know what your configuration actually is yet. Okay. You just have a concept in mind. Now, once you're done here and you've frozen your concept, and how well you did here will play out in the next preliminary design, because if you need to change a lot of things, you didn't do a good job here. Okay, so, but once you finish this, now you go into preliminary design. All right, now this is where you start looking at your subsystems across the board. Okay, for aerodynamics, what kind of control surfaces do you need? Did you look at using a novel and disruptive technology, such as putting in, you know, winglets or some sort of, you know, fluidic controls? That's when you need to look and start looking at the details of those. Now, here you also will develop your external CAD. You need to look at all of your aerodynamic surfaces, including control surfaces at this point. You want to understand your your primary design behavior, okay? Cruise, can you meet your performance goals? This is where you drill down and you use something higher fidelity aerodynamic wise to make sure that your lift and drag gives you the long-term cruise you need. When you're looking at the rotors, of course, you know, you've got to look at all the different sources of drag and things from the rotors as well as your body and see if you can indeed meet those performance criteria. You've done this in your conceptual design, but now you're revisiting, but with a higher fidelity code to make sure that you can meet those. Now you're going to look at your primary things like cruise, maybe some maneuvering, but you also want to look at some of your potential problem areas. Are you going to have to get close to stall? In rotors, you know, your collective stall, you're going to start running out of collective potentially to meet some of your maneuvers. You need to look at what the potential problem areas are. I can't tell you what they are because they're going to be what pops out from your design when you start looking at where your conceptual design goes and you start looking at some of these preliminary design things. You should start seeing where your margins to meet some of your criteria getting really small. You want to go ahead and take a look at those now rather than later, because you need to understand what your flight envelope's going to be later. We'll talk about that in a few minutes. Okay, now your timeline here is 6 to 24 months. Again, complexity drives this, as well as, you know, your RFP and how many people you've got. Now, again, I said you need some codes in aerodynamics to provide higher fidelity. This is so you can get the sufficient physics to really understand some of the nuances of your concept. So you want your tools from conceptual design. You may still use those, okay? You can still do some trade studies, especially if you need to hone in on some small features. You need a really good CAD model. Again, SolidWorks, CATIA, you know what you like, what you may have access to. Now your lifting line codes that you had before, you probably just looked at those as assuming rigid surfaces. Again, you don't have time to run a lot of aeroelastic considerations, but now you should start looking at that. Look at this early on because, rotors especially are inherently aeroelastic. If you have a wing, that could have some aeroelastic issues, and when they move, when they're not rigid, when they are flexible, that can impact your performance. So again, especially if you're close to your margins, look at those. Now, if you look at the thing I said, lifting line panel type codes with aeroelastic considerations, you really don't have a lot of time to run full up CFD. Use these what we call the mid fidelity codes, where you can, to do the broader number of points within your design of experiments. Use the higher level CFD only where absolutely needed. Okay, you probably don't have a lot of time. Computational resources is an issue, but you will likely start getting into running some of these higher level points where the physics dictate. So here are some options that you might have. Again, noting some of the things that you can have that are free or open to people with different considerations. Um, at this point, at the end of preliminary design, you've got to freeze your design. Okay, so now you've designed your wing. You've made sure that you've got your right your rotor design, what the twist is, what airfoils you're going to put there. If you have a wing or you have tails and control surfaces, you've designed those. You've designed your fuselage, making sure that you know it's aerodynamically sound, but is good enough to fit your other constraints. Okay. And let me say here too, while you're doing your preliminary design, again, I'm focusing on aerodynamics, but it's inherently in aeromechanics. So when you're doing your aeroelastic considerations with these codes, please make sure to take a look at your vibratory loads. Um, Again, I think the RCAS and CHARM level tools are what you need, but you need to make sure that you're not going to have vibratory loads that contravene your requirements. You know, do you have a sensor on board that can only have up to so much vibratory loading? If you can't make your design such that you're below those requirements, you're going to have to put in isolators. um, then isolators take weight. And so therefore you're going to have weight that you have to deal with as well. So again, a little bit of back and forth here, still within this concept. But hopefully, if you've done a good job in your conceptual design, you know, you're just making tweaks here. You're not throwing out the entire thing. You're not saying, oh, well, in conceptual design, we want a quad rotor. Now you come back and say, no, now we need a single main rotor. No, hopefully you don't have to do that. At this point, though, at the end of preliminary design, but you've frozen all of your control surfaces, your outer mold lines, um, and the actual airfoils and different concepts like that. All right. You've also got an idea of what your control surfaces are. Okay. Because again, you're working with the stability and control people. You're not doing this in a vacuum. When you go into detailed design, you're refining all of your subsystems. You're finalizing and detailing all of the aerodynamic surfaces. So for example, in preliminary design, you've got your control surface, you know what airfoil you want across it, you know how far it is, you know where it's stationed. Here in detailed design, you're actually going in and doing the guts of it, the spars, the things like that. That's not so much for aerodynamics. Although when we're modeling this, this is where you might be modeling gaps and things like that with your aerodynamic surfaces to make sure you don't have a negative impact on your performance. And here is where you need to understand the physics of your entire flight envelope, not just the ones that are problematic, but you need to go through and verify that everything's going to work throughout your envelope. Um, Again, you're working with other people, you're working with the stability and control folks, you're working with the structures folks. You need to make sure that you don't exceed any requirements that they have or any constraints that they have. Again, your timeline is complexity driven, 1 to 5+ years. Uh, and you're going to use probably those CFD tools that you had before in preliminary design. Uh, and you're going to be doing aeroelastic analyses, full CFD, CSD analysis. You're probably going to be using some form of wall modeled LES when you have the big separated flows. Uh, that is basically when you're running this, and we'll talk about this in a minute with turbulence models. This is where you're going to go to your either your detached eddy simulation or a full up subgrid scale large eddy simulation, but probably in the wake, you're not going to do it right to the surface. You don't have the computational resources for that. But you will be looking at more detail, making many more of those runs. Okay, so at that point, when you're done here, you're ready to go to production. You should be ready to go to production. So this is all the nitty-gritty details. Now, let's talk a minute about rotorcraft and what are the aerodynamic concerns here. I really like this chart. It's from a good friend of mine, Frank Cardona, who unfortunately passed away fairly recently. But you'll see this in many incantations for presentations all over. It's really great because it tells you, using a single main rotor, what the main aeromechanic considerations are. And you see this in very complex flows. You have very low speed flows here that will lead to stall. It's dynamic because, of course, you're moving. Then out here, you have transonic flows. So you're going all the way from incompressible flow to transonic flows. You have interactions because you're rotating, you're going to run into your wake. And that's going to create a lot more problems. Again, you have to work with the other folks, the structures, stability control, acoustics folks, even ride handling qualities people. You have interactions not only with your wake, but you'll have potentially rotor-rotor interactions, whether it's multiple rotors or rotor tail. You'll have wakes that going to impinge upon your fuselage. You need to look at those again, ride quality. And all of these will create drag and other component loads that's going to impact your performance and your handling quality. So, make sure that you look at this. Farther on, when you get to the detailed design, you need to look at fatigue and things like that when you're designing your final structure. So these higher frequency loads are going to create a more strenuous fatigue life. So you're probably going to have lower lifespans. We all know that vibrations hurt us with fatigue, so that's going to drive what kind of materials you're going to design with. Now, again, I'm not sure who's on here, so just a quick brief view of the rotor disc. So this is for example here, this is a two-bladed rotor. It's rotating in this direction, the standard US counter-rotating, counterclockwise rotation. The disc, the velocity is coming here, so you're flying towards the top of the screen. So your wind is in the opposite direction. We typically denote this circular disc in various ways. It's a circle. So we have quadrants, 0 degrees, 90 degrees. This is the first quadrant. The second quadrant goes from 90 to 180. The third from 180 to 270. And the fourth from 270 to 0 again. All right, so the problem is our flow varies in all of these different quadrants based on physics that we see that we'll talk about in just a moment. We also have then the advancing side, and this half of the rotor will see then the highest speed. So think when you're going faster, just in regular fixed wing flight, this is where you're going to see that. You'll see your fastest speed on your rotor will be right here at 90 degrees. Then on the retreating side, then your free stream velocity is working against you. Okay, so here what you'll see is that the velocity that your rotor blade sees is u infinity minus the rotation speed. Okay, so you're going to be going slower. On this advancing side, you're going to be at small angles because you can generate higher lift with that higher speed velocities. On the retreating side, however, you have lower velocity. So that means that, of course, you're going to have to pitch your airfoil up or your rotor blade up So higher angles of attack, and this is where you can get into stall considerations. All right, if we look at the blade aerodynamics in hover, we see everything is all the way around because your free stream velocity is 0. So it doesn't matter what quadrant you're in or whether you're on the advancing side and the retreating side. It's all, axisymmetric at this point. All right, so that makes things easier for us. And that's good because hover is going to be one of your main design areas that you have to look at. Now, if we increase the forward flight speed, then we'll start seeing some variation. So here's an example of the variation of the flow. This is the advance ratio of 0.4. Here's how you calculate the advance ratio. When we're talking about rotor speeds, we don't typically talk about your free stream velocity so much. We talk about the advance ratio of the rotor. So this is just then the ratio then of the free stream velocity. This is whatever you're tilted at for your angle of attack. Just for now, let's assume it's 0. So it's the ratio of the free stream velocity to your rotational speed. This is, of course, your standard rotation. This is how fast, what is your angular velocity, omega, times then your radius of your rotor blade. So this gives you the velocity at your tip. So it's a free stream velocity over the velocity at the tip. Now, as I said, based on whether you're on the advancing side, which sees the highest speed, and then your retreating side, you see it's going down. You can see it's actually 0, and then it actually comes into a reverse flow. So we're used to seeing a forward flow, which is this green thing. If you follow my cursor, you can see where I'm at. So this is the way we usually are looking at when we design airfoils and design wings. In reverse flow, however, we have this area where the airfoil is flying backwards, essentially. So, it's the velocity is coming from the forward flight velocity is coming from the trailing edge to the leading edge. So now you have essentially a bluff body. And again, if you look at the variation of your speeds, you see that you can go all the way from close to 0 all the way out to the very highest speeds when you can go into transonic flow. I'm not going to talk too much about that today, but there's some great books that I'll have at the end of the uh, lecture. Now, if you increase your advance ratio, you see that area of reverse flow gets larger, and that can be problematic because you need to pitch up that airfoil, and you're also going to have then tip vortices that are interacting here. I've got a great picture for you in just a second to show you that. So you've got interactions that are going to cause vibratory loads and that are going to degrade your performance. So you need to keep that into account when you're designing things. Now, on top of all this, remember your blade's not rigid, okay? Um, you're going to have then blade motion. One, because you're going to have to be changing your blade so that on one side versus the other side, so that, when you have 0 degrees on the advancing side and some angle of attack on the retreating side, you're going to have to control that. So we have then 3 types of motions. We have your pitching, which is like your angle of attack. We call that the torsion angle. Then we have our flap angle, which is basically, think bird flapping, you're going up and down. And then the lag angle, if you have an articulated rotor, it's going to have motion in this direction. Now, you may not be doing a full articulated rotor. You may have something that's more like a propeller or a prop rotor, in which case you're going to be doing a subset of these. But you're going to have some sort of control if you have a propeller or a prop rotor or a rotor flying in edgewise flight. So you're going to have some sort of control to mitigate those vibratory loads and to make sure that you get the performance that you need. Okay, so keep this in mind. You've got all of these things to worry about. Now, here's a great example of a rotor wake. This is actually just snapshots from a movie done by my colleagues at Onaha. And you see here, this is what it looks like in forward flight. So you see these these tubes here, that is your tip vortices, and you see they come around, and you see that they come close to and actually hit the rotor blades from, or the other rotor blades as they're going around and round. And you see too that they come through. You also see then that you have a vortex sheet being shed here. It's not simply at the tip, they're all along here. And if you have any discontinuities, you're going to see more wakes. You see it, here's another tip. This is a root vortex coming off the root because it's a finite blade. Now this is looking at it head on. If you look at the side view, you see that it's at some angle. This angle changes with your advance ratio. It's known as the skew angle. And you have to be careful because you don't want to have, your main part of your fuselage or your tail immersed in this very complicated, unsteady flow, because of course then, not only your aerodynamics degraded, but also your handling qualities and your vibrations are really high. All right, now going back to hover, this is important. Thank goodness it's axisymmetric because this is likely one of your design factors that you have to look at here. Here, if you're going to be doing VTOL operations, which of course we are, especially in takeoff, you're at your highest gross weight, you have your highest payload, and so you need to be able to do your operations vertically in this area. So typically what your goal is to obtain the highest thrust with the lowest required power for your rotor. Now your rotor is key here. If you have multiple rotors, typically what we do is we say, just do a simple algebraic division. If you have 4 rotors, take your gross weight and divide it by 4, and that's what each rotor blade would have to do. Now, with this, you can do at the very beginning in your preliminary design, simple momentum theory is good here. It's certainly to start. And you see that, you have a thrust that you want to generate. You have a slipstream, and that generates then a downflow. Now, be careful with this. Something else that you want to look at is you're going to be having ground operations where you're going to have people coming up to your vehicle to get the rescue material, things you're delivering and things. So your downwash there, this velocity here, it probably can't be too high. There are guidelines from military and FAA that give you an estimate of what velocity needs to be the maximum that you can have and still have people running in and out, because you don't want it to be blown away. Also, if you're landing in unprepared surfaces, if your downwash is too high, you're going to be picking up rocks and whatever is there, cans, things, and they can be picked up and recirculated and come down back into your rotors and cause damage. So you need to be careful with that. So it's not simply your performance, but keep in mind that you have other criteria such as this downwash or download that you have to deal with. Now, this is with hover. And so when we talk about that, we use a measure of the hovering efficiency is the figure of merit. Okay, the figure of merit is a ratio. It's an efficiency ratio. You'll never get above 1. And actually, you're never going to come close to 1. All right. So I want to go back to this figure that I had before and show you. So this is what a figure of merit looks like. You see that it increases with your thrust, which is typically generated by, increase in your angles, your torsion angles, collective, we call it. But at some point, you're going to reach your the maximum you can do, and it's going to come back down. So it's very much like just traditional airfoil wing stall. That's the same thing as here. What I want to point out here is something very important. All right, so look at all these things. This is where people were comparing different codes to see how close we could get to an S-76 rotor. The experiments in the black circles, these gray boxes are CHARM. Now remember, CHARM is a lifting line panel code. Okay, it's a free weight code. And this, you see that it's right on top. Okay, so we look at these two different things. And then we have traditional CFD. The one called Narducci is running overflow, which is a structured CFD code with what we call is an industry level code. It's about 50 million, I think, is what he had number of points for the rotor. And you see here's this line. So he's not up here. And in fact, you see Charm actually does better. Okay, caveat there. Uh, White House is one of the developers at CDI of Charm, and so they get the best answers. I get mixed when I've used Charm. Sometimes I get great results like this. Sometimes I'm more like where the overflow results are. But again, it just depends on what you're doing. More about that in a minute. Now, I have two overflows, two CFDs, because I want to demonstrate something to you. One, and this is Jane Helios, but it's essentially overflow, so don't worry about the Helios part here. That's in these green circles. Look how much better he is in predicting this than the Narducci results. But let me tell you why. It's because he's using 2 to 300 million points as opposed to 50 million points. So his cost is astronomical. And in fact, we use these results right here to tell us this is basically as good as we're ever going to get with the CFD using this particular code. All right. Now, bringing into here, here's something that actually combines the two. This is what we call a hybrid code. This is actually from my group, just for transparency. And so we took an industry level code, made it industry level mesh, made it even coarser, combined Charm because it'll help us with the wake modeling. And so you see, we took this and we did a mesh that is a fraction, typically half of what the Narducci industry level mesh was. And we were able to get these results, okay, in red. All right, so down lower, we're more with the CFD, but as we go up, we do closer to what experiment and everything else is getting. Now, it's not just the mesh here, but the fact that we have the Charm, it sets up the wake faster. So those results, especially down in this range, were approximately 10 to 15% the cost of the Narducci, which was 1/6 the cost of Jane's stuff. But it still pales in contrast to the 30 to 45 minutes per point that's done by White House with Charm. So you see, you can throw a huge amount of resources at it and you can get close to the results. But if you don't throw a lot of resources at it with URANs, you won't get close to the results. And sometimes simple things are closer. So this is why please don't just jump into URANs without understanding the nuances of this. Okay. Um, Now, if we go to climb and descent, we've got to add some additional things. This basically is just momentum theory with the actual speed that you're going. Now, be careful in descent. You can run into problems such as vortex ring state. I'm not going to touch that today. We don't have the time. But it is a dangerous situation. So please be aware and try to avoid vortex ring state. There are ways to do that. Now, before you do any level of computational aerodynamics, please, please, please take this in mind. Understand, what do you need from the simulation? How many simulations do you need? What's your timeline? And then what are your computational resources? Do you have high performance computing from somewhere, or do you have a local cluster, or maybe even just a PC? What are your human resources? How many people can work on this? Choose the best tool and approach. Don't go just because somebody says, oh, we're doing this. Hey, you can get great results without having a ton of resources. Trust me, you can. Invest in a good CAD model and mesh. If you don't get a good mesh, even with some of these panel codes and lifting lines, if you don't pick the right number of points and everything, you're not going to get a good result. Okay. Use best practices. Look up to see what other people have said are good practices. See how well they've done. Is their accuracy the kind of accuracy you need? Use that to guide what you're doing. Then, before you make a whole bunch of runs, please make sure you're running your code right, whether it's a charm code, RCAS, or overflow, or one of these SU2 very complex codes. Confirm you're going to get the right level of accuracy. You need to identify a problem similar to your case and you use it as a validation case for yourself and for others, not external to your team, but even to convince your team that your answers are good. We always have to prove with computations that we know what we're doing. You want to verify and make sure you understand what inputs are best to use. There's lots of knobs and whistles on these computational methods. Make sure you're doing the right ones. And then I want you to, though, be careful because you don't want to get sidetracked and go down a rabbit hole. Most of these validation cases are subscale models, and they're done typically in wind tunnels. So you've got wind tunnel effects, you've got mounting effects, and you've got scaling effects because you're running at a lower Reynolds number. Make sure that, don't get sucked in because you're doing transition modeling, which is another issue in and of itself, with a small scale model. Try to pick something that avoids those. Sometimes you can't help it and you have to do this, but then you have to show that your full scale goes up nicely. The other thing is you can't use the same mesh for a subgrid scale model and a full scale model. Why? Well, no, sorry, I think I'm going the wrong direction. Um, well, you can't do that. So first, though, let's step back and look at the CAD. You have to work with your design team on this. You need a CAD that's watertight, no gaps. Your design people don't care if there's gaps. You do. So make sure that it's watertight. Make sure that your CAD includes your aerodynamic surfaces. You don't care about rivets and bolts and details that the design people care about. You don't care about those. They're just going to cost mesh and computational worry and annoyance. So you're going to be removing details. Know what details are important for what you're doing and what details are not. Okay. Uh, quick thing about surface meshing. Here's your CAD for a rotor blade. You have your root, your tip, your leading edge, and your trailing edge. This is what it looks like when you've meshed it. Excuse me. I'm using this is actually an unstructured mesh that you'll see in a minute. So here's some guidelines. You want to, in general, make sure that you don't have your growth so high that it's impacting your simulation. Remember, you're solving PDEs inside of your simulation. If you're running an unstructured mesh, hopefully it's sophisticated enough to use mixed elements. You want to use quadrilaterals, not tets, near the surface. The boundary layers you want to resolve as well as possible. And in fact, if you can get away with it, please use a structured mesh for these kind of blades. Because then you can go to a higher order scheme and use fewer mesh points and they're faster. So if computational time is an issue, deal with the more complicated mesh that a structured code requires. You need to cluster where you expect to see rapid changes in the pressure. Okay, remember we're integrating pressure coefficient to get our aerodynamic coefficients. So you need to have a lot of points in those areas to capture how they're changing. These again are rules of thumbs. So here's an example at the trailing edge. This line right here is actually the tip. And this right here, this area right here, that's actually the cap. That's what's going on at the tip. So you've got this and the tip cap. So that line is this point right there. At the root, you need to do something similar. Okay, so here now you see we're using structured or quads out in this area, and we're only using the tets where we need them to do those other surfaces. So that's the kind of things you need to be looking at to optimize. For your volume, Avoid large changes in cell size. Your growth should be 5 to 25%. Watch your cell aspect ratios. If you know you're going to have separation or transition, you need more points in those areas. Again, mesh extents, they have to go out far enough so that you don't have reflections, potentially, depending on your code, from your outer boundaries. Take a look at things like this, okay? And of course, you need to have a sufficient points in the boundary layer. This is where that extra points in the mesh refinement we saw is important. You need to have 20 to 60 points in your boundary layer to capture what's happening, especially if it's going to separate. Turbulence models. Okay. No separation. Splart Use it. It's great. It's most economical. Moderate separation. Use a two-equation model. I recommend you use something that has a limiter, such as an SST model. And if the model has rotation corrections and other corrections, go ahead and put them in. They're there for a reason. If you have large separation, you need to do wall modeled LES, or at least detached eddy simulation. Again, I won't go into this, but there's lots of papers, and I'm happy to share if you want to see them, that if you use RANs at the surface, then you can, and LES or DES external, you can replicate things that very close to LES. So you no need to run LES all the way up to the wall. Now, typically, you'll see, why don't you just use a wall model like we talked about instead of the RANs? Well, a lot of those reasons are because we're doing overset articulation, so we have to trim. And those things are very complicated, and it's easier just to use what we call CFD, CSD coupling. Now, again, a lot of people say, is a RANS mesh too coarse? Well, but remember, what you're doing is you're resolving the scales that matter in the wake. You're not trying to model the Kolmogorov scales next to the surface, okay? Also, make sure that your code is Galilean invariant if you're running a rotating system like rotors. Separated flows, I've just gone into this. This is one of the examples I told you. Here's RANs. See how off it is from experiment, and then we've used this RANS LES approach. It's right on top of it, so hardly any change whatsoever, and you can see what the difference is here. It's really a great thing to look at, and here you can see the different approaches in the wakes. LES is a true subgrid scale model. You see it matches the experiment better. DES is kind of a compromise between the two. So if you just want aerodynamic quantities, DES or DDS is fine when you're running these. If you need to see the interactions, then you might want to do a subgrid scale model. Although if you have enough points, DDS is fine. Fuselage drag. Remember, you need to minimize drag for forward flight. Here's a great case. If you're looking for the test cases, the Robin fuselage is a standard one we use. Again, look at this. You see the separation, and you need to check out and make sure your code is doing good. You're modeling moving frames, so you're going to be in different frames. So we typically use overset. I think most things are. There's a few out there that still use sliding meshes. We don't typically use those too much. Dynamic stall, you're going to have separation everywhere, and look at, you're going to be capturing these interactions here result in these kind of separation zones, which can impact your drag. So you need to look at all of those. Here's an example of dynamic stall, and you see looking at different types of approximations here. They can impact performance, so be careful. Interactional aerodynamics, look how complicated that flow field is. You're going to have unsteady pressures on your fuselage. This is what we're trying to model here. That's typically what you're trying to model. If you're doing rotor to rotor, this is a newer area that's still being investigated. If you're looking for good experimental results, check out Georgia Tech's with Dr. Jürgen Rohrleiter's his experimental works. He's got some great things. Be careful. You see, here's a difference. Here's an isolated rotor. Here's when you got multiple rotors. You've got forward, and then you've got the ones on the behind. So you can't just do one rotor and apply it everywhere. You've got to look at them. And here's an example with Charm to see you've got two rotors. You can see the interactions. If they're closer together, these blue interactions actually start interacting together and will impact your performance. Prop rotor wing interaction, if you've got any of those, be careful and look again to see you've got, based on your rotation from side to side, you've got different characteristics there. And depending on where it's at, you see completely different analyses. So again, typically for this kind of thing, if you need to capture it and to capture the loads correctly, you're going to need a more refined mesh, and you're going to need to use that DDES or LES as well. And rotor trim becomes important, especially in rotor mode. We're actually doing some of that now, and we're finding that that plus the aeroelastic behavior of the rotor is key in capturing these interactions. Look at your innovative technologies. These are just some you might want to consider. I'll let you freeze the the thing. Here's the recommended text. If you're doing aerodynamics, I highly recommend Gordon Leishman's book. That's really, really good. If you're learning about aeroelasticity, then in general, this is a great one. Otherwise, if you're just looking, if you need the rotorcraft one, Wayne Johnson's book is very good. A good overview of computational applied computational aerodynamics is the Cumming book. So those are also very good texts. And now I'm happy to take any questions you might have.
Thanks, Marilyn, so much. So much information here. As a
Yeah.
reminder, folks, we are recording the lecture, and the resources that Marilyn has shared here will be available to you on our website. So stay tuned for that. We have a couple of questions that have come in. What tools, methods would you suggest for determining blade count or solidity?
Oh, you can do that just with a blade element theory or blade element momentum theory, depending on whether your key criteria is hover climb or forward flight. Forward flight is blade element theory, but you can use blade element momentum theory in hover. But you should be able to do your blade count with something like that. You don't need CFD for that, and solidity as well.
And just a reminder, folks, you can use the Q&A function in Zoom to post any additional questions that you might have right now. Other questions we have coming in are, can you share your thoughts on a coaxial configuration setup to offset the velocity difference between advancing and retreating flow, as in retreating blade stall?
Right. Okay, there's some really great experimental results out of Jayant Sorosi's group in Texas. I think he's the one at Texas A&M. And he's got some great experimental work to show how you can do, you know, co-rotating, counter-rotating. You can offset the different blades to optimize the flow so that you get the best flow through those blades. In terms of getting rid of some of those other things, it's hard to say. You have to look at it by how fast you're going. What is that advance ratio? But take a look at those papers, and if they don't give you the insight you're looking for, feel free to send me an email and mention this question, and I'll try to help you find something else. But I do think Sarohi's work, he's been doing work for at least the past decade and is doing a really great job. He's where I go when I have questions.
Um, is there any CAD for density amplification by the organizing absorption of mass versus density de-amplification by the disorganizing and repulsion of mass in sphere shell dynamics, where the neutral zone can be through Bernoulli's equations?
Oh, that's way beyond this this talk. I think this is more of a structures type question that I think. I'm not sure where it's coming from. I would have to do some research on that one. Um, but this is well beyond this generalized talk. Um,
Okay.
I've had no problems. It sounds like you're doing some sort of innovation technology. I'm not sure, but the CAD that I've mentioned, SolidWorks, and the ones that come with some of the commercial software should be more than sufficient for this GoAERO project, unless you're using some sort of an interesting, innovative technology.
Okay. Do you see any potential of swirl recovery vanes for thrust-borne flight?
Well, it depends on your configuration. I mean, are you trying to straighten the flow before it hits the fuselage? Is that the goal? It depends on what your goal is. Is it a coax? Again, I refer you to Sarohi's work in designing your coax. I think it really depends on your design, and it sounds like this is something you might not want to ask. Again, if you want to shoot me a question with the specifics, I won't help you design it, but I'll try to tell you where to go.
So perhaps, Kathy, if you'd like to clarify here, we can also try and address it live, or you can follow up via email.
Yeah.
Another question is, if you'd like to, can you share your thoughts on distributed propulsion versus a traditional helicopter, i.e. one or a few large rotor blades compared to numerous smaller rotor blades?
Oh yeah, there's lots of here and there. And again, typically distributed propulsion, you're looking electric. Um, but you know, so with the smaller blades and distributed, there's option, you'll get away from a lot of the problems with the larger blade and the inertia and maneuvering type things. It can be quieter as well, depending on what your rotation speed is. If you have more and you can reduce the rotation speed, then you stay out of the transonic zone, and that's really good for acoustics and vibration. um, the negative, of course, is battery weight is terrible. You probably need to have a longer wing and things like that, so that's going to add to your weight. Again, it kind of is, what is your goal and what is your configuration? Um, I'm not opposed to it. You can see from some of the things we've done in our design. I think some of the uh, distributed electric propulsion is better than a single main rotor. But again, it depends on your use case and your actual design that you're coming up with. But yeah, don't throw it out. Don't throw it out. And I'm not gonna say bad things about DEP. There's, maintenance and things like that can be a problem. But what is your goal? What is your use case?
Marilyn, this is probably going to be our last question, but this is actually the follow-up to the SRV question previously, where you were asking for a few more specifics.
Mm-hmm.
So the innovator is stating that the goal is to improve propulsive efficiency by recovering tangential thrust vector without the coaxial rotors.
Hmm. There's been a lot of there's been a lot of work in looking at that using fluidic type actuators. Um, you know, Putting fluidic actuators on a rotating system is problematic in and of itself, because you you're probably going to have to take your power source, which is in the Eulerian frame, and move it to the rotating frame, which is not trivial. Although there are um, some things called compact that were Ari Glazer at Georgia Tech is one of the developers of those, and that doesn't need anything. It's compact in and of itself. um, and you can orient those so that you can you can achieve some recovery of things. There's also some, winglets, not winglets, uh, what do you call those? Little fences and things. The negative on that is that they tend to add drag. And if it's something that can be deployed, especially if it's passive deployment, then I think you've got a chance on it. But that's always the key. Those are the holy grails. You need it in one area and not in another area. And can it passively deploy, or if it's active, does it by itself on the vehicle due to the weight and the cost and the maintainability of it? But there are some options. I think take a look at the compact if you're interested in the fluidic actuation. Because I don't think, at least for the GoAERO use case, survivability in when I say survivability, I'm talking about enemy fire and things looking at you. And so compact actually might be something decent if you have the ability to put up with some of the extra drag. You can look at fences and other kinds of um, things like that people have looked at shark skin mainly in the streamwise direction. But if you're going outboard and trying to cap that, those are passive actuation based on what's happening, and you could potentially try some of those. It's a very difficult problem because the trade-offs are really bad, because it usually impacts you in hover, and that's usually one of your main design criteria: getting off the ground with your maximum gross weight and doing your takeoff. So, but good luck. If you have something specific where I won't impede upon your design, I'm not with another team or anything, but I'm trying to be independent, and I don't want to, advocate for one team over the other. But I'm happy to answer some generic questions if you can give it to me without your specific design.
Thank you so much, Marilyn. We're just slightly over time, so thank you so much for taking all of these questions. And as Dr. Smith has mentioned several times, if you do have other questions that you would like to reach out to her with, she has generously provided her email address for more support. As a reminder, our submission deadline for stage 1 is next Wednesday, December 11th at 5 p.m. Eastern Time. We've just sent out another reminder today with necessary details. Please keep in mind that no late submissions will be accepted. So please be sure that you are online, registered, and completing your submission form in a timely manner. If you have questions, feel free to reach out to us at info@goaeroprize.com or utilize the forum. Many people have posted questions there regarding specifics, regarding the submission itself. So we encourage you also to search through the forum because your question may have already been addressed. Thank you again, Marilyn. We really appreciate it. And the recording will be posted. And we look forward to your continued involvement in GoAERO.
Great. Good luck, everybody.